in the second session of this program. Now I would like to introduce today's presenter for this session, Mr. K. Shiva Reddy sir. Sir is also the alumni of GEC Bilaspur 2007 batch from the Information Technology branch, and presently he is serving as a scientist engineer at the Department of Geoinformatics in the Indian Institute of Remote Sensing. He holds MTech in geometric engineering from IIT Roorkee. He has the expertise in the field of geospatial software development and health GIS. He is actively involved in teaching and R&D activities in GIS, web GIS, programming, data mining, and databases. He is a QGIS Shri contributor and the author of popular QGIS plugin Q Real Time. We welcome you, sir. We have great pleasure to have you with us in this 5-day FDP program. Now we will start our session. So before starting that, if anyone have any question during the presentation, please raise your hand and your control panel. We also have question answer session at the end of the presentation. So without further ado, the space is over to you, sir. You can now present.
Okay. Thank you, madam.
Okay, sir.
Okay. So we just we'll have some context switch. So today class we'll discuss about what is GIS, and we also understand how we can do data inputting in GIS. So basically, the learning objective of this class would be more towards the learning based, means at the end, a participant should be able to define what is GIS. He should be able to model different geographic phenomena in GIS. So it will cover more fundamentals, so that at the end, those who are new to GIS or seldom use GIS, they can have better understanding how we can model different geographic phenomena in GIS. We'll also understand basic concepts of digitization. Of course, my colleague, I think tomorrow or 2 sessions later, will cover a detailed demo on QGIS. So before that, you'll have a basic concepts of how digitization works. And at the end, I will introduce with the advanced data collection methods where you can use smartphones and other for making data into GIS. And there's some work we at IIRS also have done in that field. So that will also be covered in today's lecture. So I request a participant to feel free to interrupt anytime. You can raise your hands or ask any question so that it will be more interactive. So we'll start with introduction to GIS and geographic phenomena. So GIS, there's different definition, different perspective. So today we're going to see as a system perspective of information system perspective in that sense. So geographical information system is a information system which consists of, any information system consists of 2 parts. One is database management system and second is tools. So normal DBMS only provide tools to store data, right, and retrieve. While when you add on top of DBMS, if you add tools, so based on the tool, information system definition will change. Suppose I am using MIS, Management Information System. So I will have a DBMS and tools which are required by management. Management, say it may be summarizing, it may be aggregation of the various data and having different hue. So if tools are related with the management, it become MIS, Management Information System. Similarly, if these tools are related with the geographical data, it become GIS. So there are 2 unique things about GIS here. Unlike other DBMS, we have special kind of data. Also, the tools and visualization, presentation, everything is GIS is different than the other branch of the information system. So other information systems digital support system may look similar, alike. That's why there are many players, many software. While GIS, we see there are subset, very few players which are available. So GIS is a information, again, is basically an information system. It means we store data in digital form, and it provides tools for not only data collection, storage, analysis, and presentation. So GIS acts as a single stop solution for all your requirement of handling geographical data. the data may come from the remote sensing, data may come from the ground-based survey, data may come from the photogrammetry and other techniques, but GIS will provide you comprehensive tools so that you can, from the data input to data analysis to at the end, you can make a beautiful map, or you can extract information in terms of different graphs, and that can be further used. So this is short about GIS. So then, because I am talking about data here, so we need to understand how data is organized in GIS. Of course, next session we will be having a more detail in what format data can be stored, what are the different ways in GIS. But today's this class, what we want to understand is how data is organized in GIS. So in GIS, as we understand, there are two components of data. One is spatial, another one is non-spatial. Non-spatial data is also called as attribute data by the most of the GIS users. So in non-spatial data can be which are not related with the location. So these data are common in other database also. So generally we define non-spatial data, attribute data into this category. One is nominal and ordinal. These are like when we have nominal data means they have categories. Like we have agriculture, forest, these are nominal. Ordinal again is again a nominal, but it has the order. So when I say small, large, medium, or when I say rank them, so these ranking have some link. So when I say dense forest, sparse forest, high rainfall, low rainfall, so they are again a category nominal, but they have order. So we know that high rainfall have higher rainfall than the lower rainfall. Other category which we generally have in attribute data is numerical data. So it can be ratio or interval. So basically numerical data ratio means the difference. Like ordinal, we have, suppose we have ranking like low, medium and high. So there is no distinction between what is the difference between low and difference between medium and high. While in the ratio data, interval data, you will have an equal size interval. So you know, if I have a 1 degree, 2 degree, 3 degree and 4 degree, so 4 minus 3 is also 1 degree and 3 minus 2 is. So each interval has an equal size. So that's why they are called interval data. And it's again, ratio data is a subtype of interval data where we can actually define the absolute zero. So basically for understanding purpose, we have attribute data which are either can be nominal, ordinal or numeric data. So this is not new. This is being used in database long time. So this data, so GIS data consists of all the traditional data which we attribute data which we generally store either in the spreadsheet on tables. Apart from that, the unique thing about GIS is it has a spatial component and both are linked together. So spatial data, we have two kind of representation. We can either represent as a raster or as a vector. So the raster is like, it will cover, suppose you have a study area. So what will happen is raster will cover entire area. So there will be no blank places. There will be, whole area will be covered. So bigger the study area, bigger will be the raster data. And entire area is divided into uniform grids. So say uniform grid in the sense the grids can be a rectangular, square or any uniform shape, but it will cover entire area. So then it is called a raster. So good example of whatever images, satellite images, the photographs which we capture from our smartphones, they are all kind of raster data. So raster data only disadvantage is that if you have a bigger area, it will cover entire area irrespective of you have data or not data. So it only depends upon the extent. And second component is called, second type is vector. So vector data are generally suitable where we have our area of interest within study area, we have small features which we want to store. So this vector data can be point, line and polygon. This is a basic geometry. So point data will store only x and y pair. So this xy can be a latitude, longitude. This xy can be a coordinate in any projected coordinate systems like UTM or something. So it may be in meters or feet. So unit can be anything. So but point will define by the X and Y. While line, when we have a linear feature, as we understand in mathematics, the line are like one dimension where we don't have width, only length is there. So in that case, line can be used to they are group of XYs joined together and sequentially make a line. And third type which we can have in GIS is called polygon data. So polygon data are basically similar to line, but they are enclosed. In the sense, the start and end point will be same. So they will be covering a area within the boundary. So this is called polygon. So in GIS, your data can be modeled as either as a point, vector data, suppose you are modeling as a vector, or line or polygon. In the sense, if you want to store say location of restaurants in your city, so you can make a restaurants data file, vector file with the type as a point. So within that file you will store all the points which are which represent the location of the restaurants, and corresponding to restaurants you can represent any attribute data. But what is not allowed is you cannot have a same this file, the vector file is called in GIS terminology we call as a layer. So a single vector layer can either be point, line or polygon, but it cannot be mix of two. So if I define a restaurant layer, I had to define it is going to store point, line or polygon. So I cannot have a single layer having two data. So I cannot have a single layer having some points and some polygons. So those who might be using AutoCAD or other softwares, drawing softwares, they may be allowing a single layer having multiple geometry types. But in the GIS, geometry type is assigned exclusively to a layer. So one layer can be of either one geometry type, either point, line or polygon. So those who are coming from other paradigm or other AutoCAD or other systems of drawing, so for them they can note that in GIS layers can be either of one. If it is a vector layer, it can be either point, line or polygon. So having understood that GIS have a vector layer and we have vector representation, point, line and polygon, second thing which we want to understand is how we can represent geographical phenomena in GIS, right? So basically this is when we try to represent a reality into a computer or digital form, is also called modeling. So how we can represent that is the art, or that is the thing which any new GIS user need to learn, so that he can easily model. Once model is there, then he can create database. So geographical phenomena can be of two type, either object or a field type. So object type means object. What are the geographic phenomena? Objects like buildings, roads. Because object means they are defined in a discrete boundary, and they are their location is discrete. In the sense, in your study location there may be 100 buildings, 200 buildings, 5 buildings, and there may be some place maybe buildings are there, some place there will not be any building. So in that case we call as a objects. So object have a clear-cut definition, and it need not to be present every place. It will be present some place, and some place it will not be there. So these are called objects, and generally most of the time we model them as a vector data. So if you want to store objects type geographic phenomena, you can use vector. Fields. So second one is field. So field is what? If a geographical phenomena field means it has a value for every place in the study area. So say when I say building, so whole entire study area you may not have buildings. But if I say field, so entire study area, every place there should be some value for that field. So in this example, if you see this hill slope, so I have for every pixel or every location, I have a value of slope. Similarly, for every location, I have a value of temperature. I have a value of soil moisture. I have a soil type. So then when this entire area have every place there is some value is called a field. Field are continuous. So like electromagnetic field or any values which cover entire area will basically represent as a field. So these fields can be of two type. One is called continuous, another is discrete. So how means if you see, if I say temperature, right? So temperature value is everywhere, slope value is everywhere, and these values are changing gradually. In the sense they are continuous. In mathematical term, you can actually differentiate. These values can be differentiable. So if you have a height, so you can by differentiating height, you can calculate the slope. So in that sense, they are continuous. So height also is a continuous phenomenon. So your data may be continuous. In the field, your data may be continuous. So mostly continuous data we represent in raster. Or there may be chances there your data you are representing as a discrete. Like here, as we discussed, suppose in numerical you have numerical data, you have possibility of continuous, but I can have a nominal. Nominal means categories. So like here, I have defining the area into different land use or land cover. So forest is a land cover, agriculture is land use. So what will happen is there will be places where the value is agriculture, and suddenly there will be a discrete boundary. After that, there is a forest. So this I can represent as a raster and vector both. If I represent as a raster, for every pixel I will say this is agriculture, and side I say this is forest. So there is a discrete boundary. But height, you can see that height values is gradually changing. It's not a discrete boundary. But for the land use land cover classes, you have a discrete boundary. So that you represent as a raster. When you divide entire area into uniform grids, which general layman term we can call as a pixel. So for each pixel we assign some value. So here we can assign the land use land cover classes for each pixel. Or we can represent as a vector as a polygons. So this we can make a polygon. Okay, entire this polygon belong to agriculture, entire this polygon belong to agriculture, this polygon belong to agriculture, and another polygon belong to forest. So fields can be represented in two ways. If field we have a continuous data, then we mostly represent as a raster. And if we have discrete data, we represent as we can either represent as a vector or raster. But objects are, of course, there is no hard and fast rule what you represent as a vector and raster, but what we are telling is efficient and more computationally efficient way of storing. So objects are mostly stored as a vector unless you have a special reason to store as a raster. And fields are, if they are continuous fields, we store as a raster. And if they are discrete, we may want to choose both options, vector or raster. So image classification, you have seen that the output of the image classification can be taken as a raster directly, or we can be converted into vectors and then store. So only advantage of vector will be it will be a lesser in the size and easy to manage. Yes. So far we understand that GIS has two types. One is spatial data and non-spatial data, and non-spatial data is called attribute. And for the spatial, we have seen that it has vector and raster, and vector data can be either point, line, or polygon. And how we can represent any geographical phenomena either as objects or a field. And so objects are mostly represented as a vector, and fields are represented as if continuous fields mostly as a raster, and discrete fields we can represent as a vector or raster. Yes. So we move ahead. Now we want to see how actually data inputting and editing is done in GIS. So in GIS, as we discussed, everything is stored as a layers. Each layer can be vector or raster. and you will see that most of the time you will be handling with the vector layer, and this vector layer can point line polygon. So now question is, from where you get data, how you if you have a data, or if you want to prepare data, how you can do the preparation, what are the how to move ahead with data preparation. So that will be the next part of the lecture. At the end, we'll also see how we can use smartphone and other advanced techniques to collect data. So manual digitizing is one way of input, where we actually have data from different sources. Like we have data from manually drawn old maps. So topo sheets may be of 70s or 40s or even 90s topo sheets prepared by manually drawn maps. So these maps, if you want to bring to GIS, because in GIS first condition is it should be in digital form. So to convert it to digital form, we can bring manual drawn maps and digitize. Similarly, we have legal records. Suppose there is no other option. Suppose you want to establish the legal, say, ownership of a land for 1950s. So there is no way that modern satellite images or modern digital ways can be used. We have to bring back and see that old maps, bring the old maps, and from there only we can clear the dispute or establish who is the owner of this land. So these legal records, which are old records, mostly 90% of them are manually drawn, manually maintained. So that need to bring to GIS. So there can be one source. And third one can be a list of coordinates calculated using the traditional conventional surveying techniques with associated tabular data. So what happened is you have calculated the measured the coordinates, and corresponding to any, suppose you are mapping a tree, so you made the coordinate list of the trees, and corresponding to each tree there will be non-spatial attributes about trees. So it's a fruit type, it's a which type of tree is the age of the tree, or suppose. So these kind of information which are non-spatial, so these tabular data we have along with the coordinates. So these data can also be inputted into GIS. And of course, as we were seen that earlier class, so there may be projects where you have aerial photographs may be taken. So in this lecture, when I say photographs, means they are analog. When I say image, they are digital. So analog photographs, like they are developed from the negatives and other technology and printed on a paper. So these are called aerial photographs. And when I say image, aerial image or satellite image, they are directly captured as a, using the digital devices and stored as a digital form. So they can be a source. So these are the generally a source, also called as a legacy sources, which are old sources which are not in digital form. Okay. So then these can be converted and imported into GIS. These are legacy sources. Similarly, we have a field coordinate measurement by surveying technique, like we have coordinate surveying. You might have some from the plane table survey to the IOP based surveys. So, or we can use total station. So these kind of instruments which either provide data as a analog or digital. Like nowadays, if you are using total station, which acts as a electronic distance measuring devices plus theodolite, right? So combining both, it provides you data in directly digital form. So that can also be directly imported into GIS. Similarly, GPS and other global navigation satellite system, as we discussed in the earlier class, from these sources, if you are getting data as a digital input, it can be directly inputted into GIS. And finally, image data means they are already already in digital forms. So either we can classify, because simple image bringing to GIS don't make any sense, because image don't tells about the features, it just tells you about the reflectors in different wavelengths. So now from that I need to extract information. So either I can do the manual classification, or I can do the manual classification, or I can do the automated classification. So I think some of the portion might be covered. So these classification results can be directly inputted into GIS, and while there may be sources from where you get the direct raster data. Means you divide your study area to universal grid, and in each grid you assign some values. So that may be done for covering entire area into any purpose, right? So there may be some scenario specific cases where you use vector, point, line, polygon. You want to create a raster and represent data. So that is also possible. That can be input into GIS. So let's understand each of them some more in detail. Suppose you have a topo sheet, and from topo sheet you want to extract information. So these topo sheets are assuming that they are created using manually drawn maps. So they have carefully drawn and printed on a paper or cloth, and they are stored. Now you want to bring to GIS. Right. So generally topo sheets will have, like most of you who are civil engineer can understand, these are contours. Each contour tells you about the height, and based on the measurement you can understand what is the height of different things here. Similarly, based on the legend you can identify different features. The blue areas represent the water. Similarly, other areas also, forest and other areas, can also be seen using the legend. So these data are there. Now I want to bring to GIS. So if I want to bring to GIS, then I have to do sequence task. First, this need to be scanned and bring into the digital form. Then we will do the digitization. That we'll understand later. So this is one source, topo sheets. Second, what we are talking about, like a field measurements, like coordinate surveying, like done from the any total station or any electronic distance measurement devices. If you know the distance and the angle, you can calculate height and other things. So this is the simple trigonometry problem. And nowadays they are automated, digitized in the sense you just use an instrument, target one thing, it will calculate distance based on the time of flight of the light, laser beam or any light, and it calculates distance and a height, distance and then angle, and based on that other measurements will be calculated. So if you know the coordinate of this point, you can easily calculate the coordinate of the remote location where you cannot reach using these kind of instruments. And these coordinates, once captured, can be imported into GIS. Similarly, we can use GPS. So one is handheld GPS. This GPS is attached with the antenna, and from there you take measurements, and these measurements can also be inputted into GIS. So now we have seen that if you want to have a topo sheet, right, and bring into GIS, then what are the steps you need to follow? Because once you want to bring to GIS means you have to extract feature and convert them into vector. So in this we have like manual digitization process. If you see, if you have a map which is a non-digital paper-based map, then you need to scan it first and bring to GIS, right? Or if you have an image, means already digital form, so you can directly bring that image. So basically I had to convert a photograph or a map into an image. So scanning is the one. Now once the image is there, so whenever we scan any image or take images from your handheld fold on any camera phones, they are not georeferenced. They means if you move your cursor on the image, the coordinates are image coordinates. They are not anyway related with the ground coordinates. So these are called non-georeferenced or non-referenced. It does not refer to any real values. They are called non-georeferenced. So in that case, suppose our case, like suppose I scan the map, so there is no way that scanner will assign coordinates to it, right? So they are not georeferenced. Similarly, if I take images from a photograph or images from any digital source which is not linked with the ground coordinates, and though it is a digital form, the coordinates are not known. So in that case, what we need to do is we need to collect ground coordinates of the control points. So as I can see that the previous lecture also, there's an example where finding the control point is difficult, you make artificial mark. Similarly, if you have an image, if there is artificial mark or some marks are there, or there is a natural features which can easily be identified. So you first, after the scanning topo sheet, you identify a special, suppose example of topo sheet, you identify features where you can easily identify that on a ground. So you identify these places on the topo sheet, and same places you need to get the ground coordinates. So these places for which you know both image coordinate and the ground coordinate are called control points. And once you identify that, you collect ground coordinates. This ground coordinate, again, nowadays we have two options. Either you go to the ground and use GPS and other surveying technique to measure the coordinates of a point, or you can go with a high resolution image of that area and identify that point in that image and the coordinate. So suppose you have a topo sheet, you identify the topo sheet prominent location in the topo sheet and go to the Bhuvan maps or to Google Maps, Bing Maps, and identify the same location and note down its coordinates. So your ground coordinates, this is the one way. Or if you want very precise locations, you actually go to the ground and identify the feature in the image, and for that you calculate the ground coordinate. So then next step is GIS provide you tools to digitize these control points. Means you select a control point in the image, and corresponding to the image, as soon as you select, image coordinates are captured, and then you enter the ground coordinates. So once you do for at least 4 to 5, or based on the transformation technique which you want to use to solve the matrix, you assign these ground coordinates in the digitize these control points, and then you transform. So based on because for this control point I know both image and the ground, so basically we'll calculate a matrix transformation matrix which convert a given image coordinate to a known ground coordinate system. And then once you apply this to entire area, you will get output as a georeferenced map. And that georeferenced map, you move your cursor any place, you will get the actual ground coordinate. So now these ground coordinates can be digitized. So digitization is simply when you digitize, you are not manually editing. Till now, while transforming, you are changing the image from image coordinate to ground coordinate and saving at the separate file. But so this is a raster layer. Now I have a georeferenced raster layer. Yes, but once we start digitizing, we are not changing anything to the image. We are creating a vector layer, either point line or polygon, and identify the feature on the satellite image or the topo sheets. We keep drawing things. So this can be done in a stream mode and point mode. Generally, different GIS software provides you different tools. So when I say stream mode, means it is like freehand drawing, where you don't need to click, and point mode you click on different, and wherever you click, vertices will be created, and these vertices will be joined to form points, lines, or polygons. So if you see what will happen, like if I scan, so there is a linear feature. So this can be the scanning. So 1 second, there's some disturbance.
Sir, please mute your mic, sir.
Problem. I think my screen is visible. I will share again.
No, sir, your screen
is fine, right? So when we are doing scanning, what will happen is, if you may once you see any scan topo sheet or something, you may see that linear feature rows or something will have boundaries like this. These are the boundaries of the pixels, right? So but while digitizing, because you want to digitize a linear feature, you can digitize from the center of the lines. So this is the job of the operator to do the scan, and this process is called digitization. So this is a hypothetical example what basically you are doing by digitization. Suppose this is the image, right? I have a different classes coded as a different color. So now I will create a vector layer say polygon layer. So because I want to convert this into polygon, so this polygon layer is blank. Now I use this as a reference and keep clicking on the boundaries of this yellow one, so that this big yellow polygon will be created. Similarly, I can create this polygon, this and this one. This 4 I can do because this boundaries are so crisp and clearly defined. This is the one way. But suppose your actual satellite image or classified image comes like this. When things are very much crystal and clear like this, you can use automated method to convert this raster to this polygon. So either you can do manual digitization or you can do automatic conversion from raster to vector. These tools are available in GIS and both remote sensing softwares. So basically what they do, they found out all the adjoining or neighboring boundaries having same values and can make them as a same polygon. Or when things are complicated, like you have a different roads and different junctions and you don't know when road will change, so software automation technique may not help, then you can do the manual digitization. So let's move further. When we do digitization, there are some terminologies which generally GIS software, if you are handling any GIS software, you may encounter. So it is better to understand them before using GIS software, so that you are not blindly following the user manual, rather you understand what actually happening in the software. So all the endpoints are called nodes. So these points here, these are called nodes. So they are end nodes, means they either node maybe either the termination of a feature or start of a feature. So basically they are endpoints. So there is a one line segment from here to here. There are two line segments starting from same point here, endpoint and this. So this is one and this is one. So there are two line segments sharing the common nodes. So nodes means they are same, but how they are different? They are different because of their vertices. So vertices define the line shape. So what will happen is the second line only have one end node here. So two end nodes and no vertices. So that's a straight line. Third one, which we are seeing here, it has a 1, 2, 3 line segments. So this line has 3 line segments, and each line segment is bounded by the vertices. So one endpoint and first vertices. So vertices define the shape, while nodes define the boundaries. Right? So in GIS, you may want to see when you want to move vertex or you want to move the nodes. So basically, vertices are the deciding factor. So now what will happen? Let's see practically when you start digitizing. I have a curvilinear feature in the map which I want to digitize. So I have two possibilities, two extreme possibilities. Left one is I just click on some places and go forward or click another place. So these are too few vertices. So I have only 5 vertices for this curve. So you may see that this curve actually don't look like a curve, but very abrupt, disturbing lines. Right? And another example is I have a very hard worker student who want to digitize and who want to take entire day for digitizing a single curvilinear. So he will keep digitizing too many vertices nearby and keep digitizing. So there are too many vertices. So both are examples where here we are actually losing information. Here we are actually doing a lot of hard work, and not only hard work, it also increases the complexity in terms of storage, because for each vertices I need to store X and Y. So your data size will increase. So basically optimal number of vertices we can choose. And this depend on, as we are seeing the last class also discussing that, depend on the project requirement. And let's go move further down to in GIS term, this depends on the minimum mapping unit. Generally we call as a minimum mapping unit. So means how much is the minimum measurement you want to do, you can do on the maps. Suppose my topo sheet is created using the traditional manually drawn, so they may be using any pointing pen or surveyor pen or surveyor pencil for creating these features. So the tip of the point is 0.25 millimeter, then that will be the minimum mapping unit. So corresponding to multiply with the scale, you get actual ground coordinate which you can measure. So similarly, you can put a threshold. What should be the minimum distance between two vertices? So automatically, if you put this threshold, so the software will not allow any vertices to be created less than that distance. So automatically, this too many vertices problem will be resolved. But too few vertices problem cannot be resolved. So this operator need to take care that wherever there is a substantial movement or wherever he want to represent it as a curve, there is no other option to other than increasing the number of vertices while digitization. So because it is manual task, so any manual work have an error, and so to avoid errors or to correct error, first we need to understand what are the common errors which can come across while digitization. So two most common one is undershoot and overshoot. What will happen is you are just short of your target, then it is called an undershoot error. And sometimes you are very you don't want to undershoot, so you end it in overshooting. So one kind of error can be undershoot, another kind of error can be overshoot. This is very common error, and if you don't use any technical mechanism to avoid it, most of your digitization tasks will be either having the undershoot and overshoot, and it may reflect bad on your project input, and you may end up in problem. These are the spatial errors. Similarly, as we understand, what may happen that if you are not enforcing that non-spatial data need to be entered, so sometime the label of a polygon or the name of some non-spatial attributes which are essential for your project may miss while digitization. Of course, GIS software provides you tools so that you can enforce that this and null entries are not possible for some of the attributes, so automatically that will be enforced. But this kind of error can also come. And there may be some error like while digitization, some software provide you when you double click, it will record as a end of it record as a node. The single click vertex, double click is a node. Some software provide you the right click option to represent the node. So what will happen by mistake also pseudo nodes means the node is not required here but is created. So that can be created. So in place of node it should be a vertices here but node is created. So that can also happen. Similarly, if I have a polygon, so polygon should exactly close at the same point where it starts, but sometime you may overshoot, and these extra nodes coming out of the polygon are called dangling node, and this arc is called dangling arc. So this can be one kind of error. And all these error can be removed. We'll see how the mechanism. So we'll first see what is the general way where one person is digitizing, another person is editing it to avoid error, and later we'll see what mechanism we can use so that most of the error can be minimized. So like in this case, if you see I have this satellite image I am digitizing here. So after digitization I can see that this polygon area I am not able to relate to anything. This is one kind of error. I see that this geographical feature I am not able to link. Similarly, if you see this one, this is also a kind of error because I am not able to link what this boundary represents. This boundary should either represent this road or it should represent this forest cover line. But it's not doing any of this. So there are two errors. So what is the first solution? You just select a feature, so this polygon, and delete it. Right? So in that case, what will happen is you again need to digitize if that feature is required, because I cannot able to find out, we have deleted it. And second one is editing. Now for the second case, this one, right? This one, what I want to do is I want to don't want to delete, but I want to correct them. So for correction, you select this feature and you move it individual vertices. As we discussed, vertices define the shape. So I want to update the shape. So I can move these vertices below. Right? So as you move vertices below, it will then this is the input. Once you move all the vertices to the right position where you think it should be, then output will be like this. So one we see that deleting a feature is one solution, but many times it is not possible because it is a very big digitization task and only few vertices are misaligned. So you select that particular vertices and move it. So that is one kind of error correction technique, and this is called editing. But as I discussed, there is a very high chance that you cannot avoid overshoot and undershoot, because in now modern day computer there is infinitely there is no limit to lower level zoom and upper level zoom. So, and we also discuss about window mapping unit which you can define. So what basically we can use is snapping. What is snapping? So snapping will basically help you whenever you move close to any point or line, automatically it will attach to that point. So that process, you're moving your cursor to the target, is called snapping. So when a vertex or node is close to a line, it is snapped, then it's called a line snapping. Similarly, a vertex or node which you are going to create is close to a point, automatically attached to that point is called a point snapping. That we further discuss here. One second. Am I connected? Am I audible?
Yes, sir. But you're not. Your screen is not visible. There is disturbance in signal.
Okay. Give me just one minute. If our data source is direct vector or raster in digital form, so there is no big issue. So GPS files you can directly bring in. ASCII Excel sheet. Suppose you have a spreadsheet which have X and Y coordinates and other attributes of a single feature. So each record, each row belong to one say point. So what basically you need to do, you need to bring to GIS and tell what is the X and Y coordinate fields, and rest all other fields will be taken as a non-spatial attributes and they will be stored in attribute data. So you can directly bring any your spreadsheet in Excel file format or ASCII, CSV, any format to GIS. If you have an already satellite image already geocoded, you can directly bring in, and as we discussed, you can use that satellite image as a background, and on top of that you can create vector linkets. Image classification outputs, as we discussed, these image classification outputs are like can be either come as a raster or vector. Basically, each pixel will have some code for class, and as we discussed, that can be easily converted into polygon, and then that is called the vectorization of raster, that you can do into polygon or into point or line, and automation converted this data can be stored in GIS. At the end, I thought let's have some summary of the advanced techniques which are being used for rapid data collection. Like urban environment, we want to regularly collect data in more frequent way, right? So suppose suppose somebody is managing the electric poles, somebody managing the telephone line, somebody managing the some utility kind of thing, where not only collection of data single time is required, but also regular revisit, and so you should have a solution which can be done rapidly. And And for that, there are many techniques. One case study I am considering here. So those participants who are interested, they can note down. It's called Open Data Kit, ODK. So they are app like ODK Collect and another project supported by UN, Kobo Collect. So they are these apps which can be easily installed in any Android phone, and they allow you to create collect point, line, and polygon from the mobile phone itself. So you can not only create point, line, polygon corresponding to that feature, because it's a smartphone. You can collect photographs. You can enter the non-spatial attributes, and also at the same time you can record the location, so you can store points. Similarly, suppose you are moving in a vehicle, so you can use this mobile app to cover a road line, or you want to distance a boundary of some place or a building, so you can move around the boundary of the building and you can save as a polygon. So that is the spatial part. And of course, in mobile device, you can enter the attribute data, you can have a drop down options, you can take photographs, so that everything is possible using the smartphone devices. So one common, so there used to be time like if you want to collect data from mobile, you develop a mobile app. But that is not feasible solution, because this requirement are generic. Like when I want to do a GIS operation, I don't develop a GIS software, I use the existing GIS software. Similarly, if you want to use mobile phones to collect data, so there are existing solutions which you can use. So one of this famous popular solution is ODK, Open Data Kit, right? And another one is getting popularity is Kobo Collect. So ODK provide a mobile app as a ODK Collect. Kobo Toolbox, they provide as a Kobo Collect mobile app. So you can use this mobile app to collect data. And what will happen is these mobile apps allow you to collect data not only in the offline form, online, but offline data can also be collected. Once you are connected to internet, you push your data into the server. The server either can be hosted by your organization or freely, like Kobo. Advantage of Kobo is that Kobo already provide you hosting service, so you don't need to bother about server. You just download the ODK Collect app. You can start your doing survey, and once data is sent to server, you can download from the server. This solution exists. Similarly, suppose you want to use ODK, so ODK Collect app, you connect to your ODK aggregate server, and from there you download, you collect the data and send data to the server. So technology behind, like similarly GIS, we have different formats. These technologies are developed parallel to the GIS. So they are not into GIS, they are developed parallelly, and they are basically use XForms. So basically you can use your spreadsheet like Excel to create an Excel sheet for what data you want to collect. So basically it's like a questionnaire, it's like a survey. So you write the question and what would be the possible answers. So either it will be text or it will be select one option, select many option. So for each question you define is question the label and also a type of the answer you are expecting. Once you do that, you convert them into a generic form. It's called XForm, XML form. Similar to HTML form, this XForm is there. You convert that XForm. Why? Because this XForm is a common standard. So what will happen is, if you convert your survey into XForm, it can be used in any software which support XForm standard. So in that case, so that is very popular outside GIS. Many people who are collecting who want to collect data like WHO people or the UN Development Agency, humanitarian agency, they want to collect survey from the ground. So they use these ODK Collect and Kobo Collect mobile apps for collecting data. The technology behind them, that is XForm. So you convert your survey in XForm, upload to the server. So as soon as you upload that XForm's survey template into the server, all the mobile apps who are connected will download that. Now, the survey form which you have created is just a skeleton which basically tells what are the questions and what are the possible answers. Now, from actual ground, the mobile app user will collect the data, and for each survey, there may be multiple submissions coming to the server. So traditional like paper-based survey, what we do is we create a survey form, distribute to everyone. Everyone will fill the form and bring you back. Then you aggregate that whole and summarize and you use in your study. The same thing here, what I am doing is in place of giving the paper-based form, I am making a digital form and putting in the server. And all mobile apps will download this form and fill and submit. So for each submission, there will be one submission entry. So suppose same form, 100 people have downloaded and submitted data, there will be 100 entries for the same form. Now, earlier paper-based form aggregation is a bigger task. First you print the survey forms, give to them, they collect data, you bring it back, then you aggregate, then again you manually enter this data into some computer system, then you generate statistics or charts out of it. So that all task has the manual intervention and time consuming. Now by using digital form, we are reducing that. So you upload this form to server, user will collect and bring that, and all the consolidated data can be downloaded as Excel sheet or CSV format. So that is the existing solution. So that because of the simplicity and the mobile app, once you download the blank form, it can work offline. So so it's a very robust solution. So a lot of agencies are started using Kobo Collect and ODK Collect apps, and these ODK and Kobo servers. Now next question is these two server and apps are ready, but if you want to do any analysis, you basically download this data. There's some summarization technique available with the server. Otherwise, if you want to do extensive study like GIS based study, you download this data, then you import into any GIS software as a commercial or open source, and then do the analysis. So the downloading, importing, right? These tasks are again manual and time consuming. So what we at IIRS have done is, because being the exclusive user of QGIS, we develop a plugin. It's called Q Real Time. It's freely available. Basically, now mobile app is already there, server is already there. This technology has been developed. So and GIS software is already there. So we developed a bridge. This QGIS plugin, if you use Q Real Time, basically you need to provide the location of this server. And so what it will do is, as soon as any data is collected and sent to the server, it will bring this data into your GIS layer. So now no manual task is required. Automatically people, because the server and mobile apps are already available, people have already collecting data. So as soon as they collect, the data can be bring back to the server. So we have option like sync, import and make online. So when you make sync on, as soon as any data is collected, within 1 or 2 minutes, all new data will be loaded into a GIS layer. So you can see real time what is the survey response, what are the data collected from the ground. This is one. Again, earlier you need to create an Excel sheet, then convert into XForm, then only a survey will be available for the mobile user who can collect data. Now, a question is, already my GIS user is creating GIS layer, right? Then he is digitizing. So what we have done is, this plugin have option like make online. So suppose your GIS layer, blank layer is already created. So you can make it online. So automatically this GIS layer corresponding XForm will be created and uploaded to the server, because you have credential for server. And so corresponding to your layer, one mobile app will be created. So using this generic mobile app, whatever your layer, corresponding data will be populated into the mobile, and user will collect data, and the data will again come back to the server, and automatically your plugin, if you sync is on, as soon as data is collected, the data will come back to a GIS layer. And third one is, there are already projects, because ODK and this Kobo technology are at least running for the last 7 to 10 years. So there are a lot of projects where a lot of huge data is collected using this technology, and they are available at the server. Either for health, either for humanitarian region, lot of data is already there. But to analyze, how to analyze that? Because I don't want to collect data, already collected data in the server, I want to bring to GIS so that I can do the spatial mapping and further analysis. So we have an option called import. So what you can do, basically you select import and select, as soon as you click import, whatever data or surveys, different surveys, data has been collected, you see the name of all the survey forms. Suppose there is a health survey, during the COVID time, this Ministry of Health and Family Welfare, they also have used ODK based technology to collect the zero survey. Means they want to understand how much is the resistance already developed in the population. So the data already collected. Now suppose you get hold to that server and you want to analyze this data, you bring to this plugin and say import and select that name of the form for where of your interest. So automatically this data will come to GIS. So in short, if you say there are already a generic mobile app available, there are already generic servers are available, standards is well defined. Only problem is these standards are not directly compatible with the GIS layer or GIS conceptual data model. So what we have done is using QReal time, we make a bridge so that a GIS user don't need to bother about anything about downloading data, is format and other thing. And same way, he can directly connect to that server and bring data into a well-known format, GIS format, so that he can analyze. And suppose he don't want to do that, he want to create a new survey, that is also possible. He can use this, he can translate his GIS layer to XFORM. So that we have developed, we have around 12,000 GIS users who are regularly using this plugin so for their data collection requirement. So those who are interested, this QReal time is freely available. You can search on QReal time in QGIS plugin. I think my colleague Prasun will have a give demonstration on how to use QGIS because this plugin is developed on top of the QGIS. So you should know the QGIS. Once you start using QGIS, those GIS users who are friendly means who can easily use QGIS, then they can install this QReal time plugin to further expand their work by integrating mobile-based data collection, web-based data collection into the GIS. So this the solution which I'm talking about, ODK XFORM, is very interoperable. So you're not linked with any one server. You can use any XFORM compliant server and collect data from mobile. It also provides, even without mobile app, if you want to collect, it provides a simple XFORM corresponding one HTML form, which can be opened in any tablet or mobile phone without the app. Also from there also you can collect. That's why we use terms like if you integrate mobile, web and desktop, these all three kind of solution into GIS by using our framework is called QReal time. This plugin is freely available, so you can use it. Yes, so that's it for today's session. So I just, before wrap up, I just want to summarize, then we may have some time to take questions from the participants. So we understand about GIS now. So we know that GIS is an information system which provide analysis, storage, presentation of geographical data. And we know that there are two kinds of data, vector and raster. Spatial part, non-spatial, it can color attribute data, and how we can do the digitization, snapping, these concepts we understand. And we also see that you can use modern technologies like XFORM based technologies, which are extensively used for collecting data from web and the mobile phones. And these data can these technology also allow you to create point line polygon. Hence, though they are not directly compatible with GIS, can be imported to GIS. And finally, we had the overview of one such project where we are trying to integrate this XFORM technology into GIS using QReal time. Yeah. Thank you.
Thank you so much, sir, for this very informative session on on the data collection and data handling of the digital survey. And now I'm inviting